We'll go ahead and start the last session. So I'm absolutely delighted to introduce my colleague and friend, Andrea Goldsmith. She's a Stephen Harris Professor in the School of Engineering, which is great. She has a long list of academic awards that I couldn't possibly list here, so it would actually just be impossible. I'll mention that she's a member of the National Academy of Engineering and the American Academy of Arts and Sciences. She's much more multidimensional than that. She's a successful entrepreneur. Already this morning, I think I mentioned that she rang the opening bell at NASDAQ. She serves on the boards of multiple public companies. She's also the founding chair of the IEEE's, it's the Board of Directors Committee on Diversity, Inclusion, and Ethics. So IEEE, as most of you know, is the world's largest professional organization with over 400,000 people. And also, I'm sure you know this, it's not one known for their excellent treatment of women, I think. So we and 400,000 other people are very indebted to Andrea for starting this effort. I should mention one more thing. At Stanford, Andrea, there's two committees that all faculty member dread being on. One is the advisory board, which is just an insane amount of work. Another one is the budget group. Andrea, I don't know if you're the only, anyway, not only has she done both, I think while serving as the chair of the Academic Senate? No, okay, fine. I mean, she did do that, just not all simultaneously. But she certainly did the two committees simultaneously, which is truly insane, and I didn't even think it was possible. It doesn't even make sense. So we don't know how it seems like some bound was violated there. I don't know. So we don't know how she does it. She's our superwoman, and let's give her a good welcome.
Thank you. I didn't know Stephen was going to introduce me. That's always dangerous. I would say that was a rather not too difficult introduction to sit through. Thank you very much for the kind introduction. So a lot of people have commented on the title of my talk. It's a little bit audacious to say I'm going to talk about the next 125 years of electrical engineering. And I think some of my colleagues think audacious is my middle name, and that's not necessarily a compliment. So I figured when Stephen said I could talk about anything, why not talk about something audacious? And none of us are going to be here in 125 years to tell me that I got it all wrong. So I'm not too worried about what I say. All right. So I'm going to give the unofficial introduction that's not in my bio. I am the product of an interdisciplinary collaboration between a mechanical engineer, who was my dad, professor at Berkeley, and my mom, who was a character designer and cartoonist for the Bullwinkle and Rocky show. And in fact, Natasha Fattal was modeled after my mom, which you can kind of see the family resemblance there. And the reason I say this is that I've always thought of engineering as an incredibly creative endeavor. And I think that I got from both my parents a lot of things that have made me successful as an engineer in thinking about the problems that we want to solve in a much broader and creative manner beyond just what's on the piece of paper in terms of the math and physics. I was an undergrad at UC Berkeley. I did all my degrees at Berkeley, in fact. And I worked at Silicon Valley at a time, I think Tom said that there's been a couple of iterations of Silicon Valley. And I actually worked at Silicon Valley in a time that wasn't a great time. This was the mid-'80s. It was after the defense industry had collapsed. This is a picture of me working actually on MIMO systems. In 1986, we were building antenna arrays to do direction finding. And the vacant lot behind me is now, this is right off Great America Parkway and 101. So there's all these huge, tall buildings there now. At the time, it was just vacant fields. Now, this company was Maxim Technologies, the wrong Maxim. It wasn't the Maxim Semiconductor Company. And it was a terribly run company. And it's always a good idea to work in a terribly run company to figure out how not to run a company. And so this company was filled with PhDs and new grads right out of college. I was right out of college. And we were working on really hard and interesting problems that I didn't have the capability to solve. But I liked the way people that had PhDs thought about prompts. They thought about them in a completely different way. So, and I also fell in love with wireless communication. To me, it was just magical, and there were all these interesting problems to solve. So I went back to Berkeley for grad school. I was actually rejected from Stanford, so if you wonder why I didn't come to Stanford, they didn't want me. While I was at Berkeley, there's no one at Berkeley working in wireless or communications or information theory, so I was kind of on my own. But I was very fortunate to work 2 summers at AT&T Bell Laboratories, which was one place at the time. It was before the breakup. And I was working with people that were actually designing a lot of the original systems for cellular second generation. So I had a fantastic experience at Bell Labs, and I came back, finished my PhD, and then I went and taught at Caltech for 5 years. So I was at Caltech for 5 years, came to Stanford in '99, the height of the bubble days. You know, it was a really bizarre time to be at Stanford because students would come to my office and they'd say, okay, I have this great idea I want to tell you about. Will you sign an NDA? You know, and I said, well, I don't sign NDAs as a faculty member, and I don't think your idea is good enough probably for me to want to steal it, so maybe you should, you know, not tell me about it. And they would anyway, and it wasn't a very good idea. You know, everybody thought that it was crazy to be a professor in wireless, because like, why aren't you out starting companies? And it just, to me, it didn't make sense. As someone who'd worked in Silicon Valley at a time that it wasn't so crazy, it didn't make sense to me what was happening in '99. And sure enough, there was the crash after that, which is kind of the nuclear winter in Silicon Valley. And then, you know, things have evolved since then. So in addition to research and teaching, which are 2 of my passions, I've done a lot of other things. I chaired the Faculty Senate. I've been involved in a lot of Stanford-wide committees, which are wonderful because Stanford is a magical place outside of the walls of electrical engineering. This is really a special place to be a faculty member, and it's been a privilege to be involved in many things beyond just engineering. I've founded 2 companies, and I've also done a lot in the IEEE, and I'll talk about some of that later. And I'm doing a lot of work around diversifying our profession, and I'll touch on that at the end as well. My best results are Daniel and Nicole. These are my 2 kids. Daniel just got his electrical engineering degree from Stanford in the spring, bachelor's degree. He's co-term. And Nicole, who was actually born at Stanford Hospital 6 months after I started on the faculty here, she is studying mechanical engineering. She's a junior. And my husband also got his PhD in electrical engineering, worked under John Hennessy and Mark Horowitz. So I'm actually the only family member who was rejected from Stanford, which is kind of embarrassing. Okay, so my research is on wireless communication. I've worked in wireless my whole career from the mid-'80s. But I don't just work on wireless as an infrastructure to enable other things. I also work on the systems that they enable. And I think going back to Jim Plummer's talk about, you know, we don't want to just be the architects of the technology that other people are using. I think it's really, at least in my own research, I found it very rewarding to see what of the technology that I developed can be used and how is my knowledge of the underlying technology helpful in building those applications. And as someone who's worked in wireless communication for, you know, 30 years, 35 years, I think it's one of the most exciting times in wireless communication, because if you look forward, what are we going to be doing with these wireless systems? It's not just about people, you know, talking to each other or watching cat videos. It's really going to enable us to do things that aren't possible that will make people's lives better, whether it's autonomous driving that will relieve traffic or allow people to drive much later in age to get around than they can today, body area networks that will transform healthcare, the Internet of Things, which will hopefully play a role in sustainability and making our infrastructure stronger and more robust and more energy efficient, and so forth. So there's many, to me, exciting things associated with wireless technology and the applications that it enables. So you might wonder, well, if my passion is research and teaching, which it is, why did I start Quantenna? Why would I go out and do a company? So yeah, this is the song.
wanna be a billionaire so freaking bad.
So that's not why I started Quantenna. It's not the only reason I started Quantenna. Actually, I didn't expect to make a lot of money because I'd worked in a startup that was not a successful startup in the 80s. So the notion that you start a company and you make $1 billion after a year or two, that was so far from any reality that I had seen in Silicon Valley in the 1980s that, I didn't think it would be successful. But of course, making a lot of money is the metric for success of a startup. So you have to want to have a successful exit because that's the mark of a successful company. But the real reason that I started Quantenna was to build something again. So I do work in theory. I do communication theory, information theory. But my first job was building stuff. I was building an antenna array and building satellite communication systems. So I spent 20 years doing a lot of theory, and I wanted to see, does theory matter? Does it make a difference when you actually build a product? So I wanted to build state-of-the-art products grounded in theory and see if that actually mattered. Is anything that I was doing in the university actually going to make a difference in the technology that I developed? And on top of that, again, it had been 20 years since I'd actually worked building things, and I wanted to make sure that the research I was doing mattered in practice. So I wanted to take the knowledge that I got out of building these state-of-the-art wireless products back to my research and teaching. So those are the reasons I started Quantenna, as well as to create a successful company. So this is March 2006, which is when we got the seed funding from Sequoia for Quantenna. And 10 years later, when we rang the bell on the NASDAQ, I actually was jumping. But the reason that I was jumping is because they give you directions. They want this to look good on television. So they say, OK, everybody should be jumping up and down. So I took them seriously, and I was jumping up and down. The person who was jumping up and down much more than me was the Japanese gentleman next to me. He was the last investor into Quantenna, so he did very well with that. So what did I learn about doing a startup? They're a wild ride. Okay, this notion that startups are all roses and champagne is so far removed from the reality of doing most startups. We were so close to running out of money so many times. There was, a lot of challenges with the co-founders, with the executive teams. We went through waves of executive teams, typically right before a tape out. It's really, and as an academic, where you're used to being kind of lauded and people think you're really smart, you walk in the door of a startup, all your credibility is gone. You have no credibility as a faculty member. You have to prove yourself. And so it's really not for all faculty members to do. It also demonstrates academics have great jobs. We have so much freedom. We're working with these brilliant students. We're working with brilliant colleagues. I mean, it's a great gig to be a faculty member. And so that was driven home to me very clearly many, many times during the wild ride of the startup. The other thing that actually surprised me is how much theory actually influences wireless system design. So when I went to my first standards meeting, Wi-Fi standards meeting for Quantenna, I thought, I'm not going to know anybody there. I go to theoretical conferences, research conferences. I'm not going to know anybody. They're not going to know me. And it turns out that they all knew me, and they knew my colleagues in wireless that were professors writing papers. They read our papers, they implement our ideas, and that was incredibly satisfying, because I wouldn't have known that if I hadn't actually gone to the standards meeting and talked to people and say, oh yeah, we know about all these developments that we're doing in the university. Often when you just sit in the ivory tower and you don't actually go out of the ivory tower, you don't realize how much impact your research has, and that was really incredibly satisfying. The other thing that was a really tough lesson is that silicon companies in Silicon Valley, and remember this was 2006, are not easy to get VCs excited about. In fact, it's very, very difficult to do a silicon company in Silicon Valley today. It costs a lot of money. It takes a lot of time. It was 10 years from the time we were founded until we went public, $170 million of investment in Quantenna to go from the beginning to the IPO. And so I think that's really unfortunate, because a lot of innovation comes out of the hardware design. And the fact that it's so difficult to have innovation in startups and hardware, I think, is going to hurt our ability as an industry to innovate. And finally, this was really disappointing. So here I had all this research that I'd done in MIMO and wireless, and we built the best chip in Wi-Fi. Quantenna's goal was to have the highest performance Wi-Fi chip. And that beautiful chip with 30 years of research cost about $5. And that's also why it's hard to raise money to do startup companies in the hardware space. Okay, so 5G is what's next in wireless. And in addition to getting much higher data rates, which is what's being promised, so you always have to say, things are going to be 10x better in the next generation. But what's really different about 5G, or the promise of 5G over previous generations, is that up until now, we've really, in building cellular systems and Wi-Fi, only been about getting to higher data rates. And now there's this whole range of applications with the Internet of Things and autonomy to go to very low energy and low latency. So low energy, if you're going to have a sensor in every device that has an on-off switch, that's got to be a very low energy wireless device that's going to connect to the internet. And of course, it's not interesting for my tennis shoes to talk to Steven's tennis shoes as an Internet of Things network. What's interesting is extracting the valuable information that we're getting from the Internet of Things and process that in the cloud, and then to do autonomy with low latency control and so forth. So that's the promise of 5G. And if we think about what are the enabling technologies, so I'm going to do a question, because I like a little bit of an interactive talk. So if you think about cellular system design, where you have a base station in a geographical region, and you blanket a city with base stations, and then you have mobiles driving around talking to the base stations. So that basic architecture was invented in a decade, and I'm going to ask you which decade that architecture was first described. It was written up in a paper. So the first cell phone systems, first generation, were deployed in the 1980s. How many people think that that basic architecture of cellular was described in a paper from the 1970s? Raise your hand. 60s? 50s? 40s? Okay, it was from the 1940s. It was a paper by D.H. Ring, written at Bell Labs, I think the year before the transistor came out, where basically that diagram is what's in his paper. So, we definitely have an opportunity to create new architectures for cellular systems. We've done a lot at the physical layer, and there's a lot of advances in technology that are used at the physical layer and in the multiple access layer, but we haven't rethought the architecture. We can go to higher spectrum, so we can go up to the millimeter wave band, 60 gigahertz. And the problem with 60 gigahertz is that power falls off as 1 over the frequency squared. So as you go to these higher frequencies, even though there's a lot of spectrum up there, it's very hard to communicate. So people are talking about using these massive antennas that can form kind of pencil-thin beams to talk directly to the device, and then you don't need to worry about the fact that you're getting this tremendous path loss if you use omnidirectional antennas. So that's great in theory, but not in practice, because if you get anything that's blocking that signal, it dissipates, and so you're not going to get a connection. You're not going to be able to close that link. So millimeter wave and massive MIMO is great, but they have a lot of limitations. There's other things that we need to look at. So if we're going to do autonomy, we need to have edge computing and maybe edge caching, because you don't want to wait for the information to go all the way back to the cloud to do the computation. And then we could also potentially apply machine learning. And in fact, maybe we should just not even worry about engineering anything and let machine learning solve the whole design problem, right? Because machine learning is going to take over all our jobs, including engineering design, or at least if you believe the hype, that's what you believe. So I don't believe that machine learning is going to take over everything. And it helps to look at some history with respect to machine learning. So it was predicted in 1956 that AI would take over everything, that there'd be machine intelligence on the human scale within a generation. And there was a lot of funding pumped in, and then things crashed. And then around 20 years ago, we extracted the valuable insights and technologies from AI. And use them in cognitive systems and other types of niche applications. And now we're right back to where we were in the 1950s, where machine learning is going to solve everything. And I don't think that's true. It has reached human-level performance, but in a very small set of areas, particularly with image recognition, voice recognition, games, obviously learning how to play chess and so forth, classification. But it isn't as dominant as people think reading the popular press. And I think there's a lot of good reasons for that. And I'll talk about in a moment how I've been applying machine learning. But the keys to the success is, first of all, we have a lot more data than we did in the past. We have better algorithms. And a big key is we have much better processors. And that's been talked about in some of the earlier talks. So it's a bandwagon today. And the question is, should electrical engineers jump on, or should we just leave it to the computer scientists and run away screaming? Because this is a bandwagon, and there's probably going to be another crash. And I'm actually usually, when something is a bandwagon and everybody's working in it, I run the other direction. I'm the runaway screaming. But it turns out that we've actually used a little bit of machine learning in our communication system design. And I think what's interesting here is the fact that domain knowledge actually helps in figuring out how to apply machine learning to a problem. So in this case, this is just a typical block diagram that you would get out of any book on communications, where you have a transmitter, a channel that you're sending a signal through. There's some noise or interference. You go through an A to D and do reception, signal detection in a digital receiver. Well, what if you don't know the channel? What if H of F is unknown? Or it's a really complex channel to solve? So for example, Viterbi decoding, which is exponential in the memory of the channel. That's a really complex decoder to put into a receiver, especially if it's a small IoT device. Or channels like nonlinear channels, we don't know how to communicate well over nonlinear channels. We only have heuristics for it. So we found that actually putting machine learning into the receiver can give us much better performance than the techniques that we've spent decades developing theory around. In particular, machine learning beats Viterbi decoding when you don't know the channel perfectly, or when it's too hard to learn the channel parameters, like in the case where you have a 100 by 100 MIMO array. So I think that machine learning is a bandwagon, but I also think that there's places where we as electrical engineers can apply it. Another thing I've done a lot of work on is coupled networks. So when I came to Stanford, I actually was interested in doing control loops closed over wireless links. I remember I had a conversation with Stephen at the time, and I said, well, if I could give you a very high data rate over the wireless system, but you'd have a lot of packets dropped, or you lower the rate and you have a more reliable wireless channel, which is better from a control perspective? And he said, what do you mean you drop the packets? That doesn't exist in control theory. We just put in another wire. If it's an airplane, we just keep putting in wires until it's reliable. Well, now that we're going to do everything over wireless, actually you do drop packets. They're not reliable networks. And there isn't a good theory for doing control loops closed over non-reliable wireless links. So how are we going to do all these autonomous systems? Are they actually going to work? That also got me interested in coupled systems. So if you have electric vehicles and you've got an energy grid and you're doing routing of the electrical vehicles, how do you figure out optimizing the routes so that they can charge up at the right places to complete their journey before they run out of charge? And IoT is also a coupled network, and so is the smart grid. So I think from my own perspective as a wireless engineer, I see these coupled networks as opportunities for us to take our knowledge of wireless or of networks and apply it to design better applications that will run over these unreliable networks. Now, probably the most far out research that I've done in my career is on neuroscience. And you might wonder, well, how did I come to neuroscience from working on wireless communication? I was part of an NSF Center. I'm the lead Stanford PI for a center on the science of information. And the idea was, how do we take traditional information technology that we've applied to communication networks and apply it beyond communication networks to economics or big data or biology? And I thought, well, the brain kind of looks like a network, so maybe I'll see what I can do there. And of course, I was not arrogant enough to think that I'd actually be able to make a contribution to neuroscience, but I was a tenured professor, so it's like, okay, I'll give it a try and see if I can come up with something. And the interesting thing is that actually we were able to develop an algorithm for seizure onset zone detection of epilepsy that beat the doctors. And so the idea is that the way epileptic seizures happen is you have a region of the brain where the neurons start oscillating in irregular ways. Because those neurons are connected to surrounding neurons, the irregular activity spreads to the next level, and then the next level, and eventually you have a seizure. Well, that's just a causal signal processing problem. So we ended up applying an algorithm based on something called directed mutual information, which measures the causality so that we could basically find out by reverse engineering back where the seizure started, where the signal started in this pattern. And this grid shows based on publicly available data, so the circles in green are where the doctors annotated that they thought that the seizure onset zone was, and the purple ones are what our algorithm did, completely blind algorithm. And so it's more accurate than the doctors if you believe that, that this algorithm is correct. And we didn't have the resources or the clinical trials to go back and do a larger experiment or see, okay, if the doctors predicted somewhere different than our algorithm, does it work or not? Because the way doctors cure epilepsy, if it's drug resistant, is they cut out a part of the brain, which is where the seizure onset zone is. So that's pretty dramatic, and so it's very important to get that zone right. And again, thinking like an engineer, I thought, well, okay, if we can use reverse signal processing to figure out where the seizure onset zone is, why couldn't we build a control loop that would basically figure out the right signal to inject right into that same region and cancel out the epileptic seizures altogether? So it's basically like a closed loop control problem, except that we don't know the system that we're modeling. It's a black box. So this was kind of a pipe dream of maybe we would be able to do this. But at the time, thinking about this, I thought, well, is this just science fiction? Is this just some dream that we would actually be able to do this? And it turns out, in fact, that we engineering, can do this now through something called medical technology. So one of the corporate boards I'm on is Medtronic. They're the largest medical technology company in the world that brings together electrical engineers and doctors. In fact, the CEO is an electrical engineer, to develop medical technology. And in fact, this pipe dream that I thought of, well, we can use kind of closed loop control to cure epilepsy. Well, we can't cure epilepsy yet, but we can cure Parkinson's. So deep brain stimulation for Parkinson's is 75% effective, where basically you use an electrical signal that you inject into the brain, and it relieves the symptoms for 75% of the patients. Another thing, which I'd never heard of before, is vagus nerve stimulation. So the vagus nerve is kind of like the backbone of the internet of your body. Basically, if it goes to all of your organs as well as to your brain, and vagus nerve stimulation can cure depression, and it can cure incontinence. So far, that's the first wave of treatments. And then there's also diabetic closed-loop control, where diabetes, if your insulin goes outside of a particular range, you die. And this closed-loop control has changed the lives of diabetics because they don't need to be monitoring their insulin on a regular basis because the closed-loop control doesn't. Now, this is for people with, I think it's type 2 diabetes, but it can also work for type 1. So a lot of exciting things in medical technology. So now let me get to why you all wanted to hear my talk, which is the next 125 years. But before I tell you about the future of EE according to Andrea, which you can't come back in 125 years and tell me I was wrong, I want to debunk a couple of myths about the early demise of EE. So the first one is Moore's law is dead. We've heard a number of talks about this. And it's true that the transistor scaling of a single transistor is not growing in the same way that it has in the past. But we have multi-core, plus we have all these other interesting hardware and device areas to look to. So I think that if you think about Moore's law more broadly as is the technology, the hardware technology that we need to enable all these systems dying or dead, absolutely not. I think there's a huge amount of work to do, and both John Hennessy and Jim Plummer's talk, I think, talked about that. What about information and communication technology being dead? I mean, that's very personal to me to say that it's dead, because that's my field. But a lot of people say, well, ICT is what drove, EE being so successful the last several decades. And now it's mature. It's viewed as, we're on 5G and wireless. Maybe it's time to move on. Well, if you think about ICT as all technologies that combined allow people and organizations to interact in the digital world, I would say it's far from dead. There's a huge amount of work to be done, not only in the communications, but also in the data centers, in data science itself, in algorithms which we develop, and the devices. So I think that there's still a huge amount of room for innovation and growth in ICT. What about the fact that nobody wants to major in EE anymore? Everybody wants to major in computer science. That's also a myth. So this data is taken from the 2017 report on the American Society for Engineering Education. Now here at Stanford, a lot of our students want to major in computer science. But if you look across the country, EE is the third most popular major. The most popular major is not computer science. It's mechanical engineering by almost a factor of 2. Number 2 is CS, and EE is close behind. So it's certainly not the case that our students don't want to major in EE. And so I was chair of the student committee in the Department of Electrical Engineering, and we did a survey a couple years ago, why did you pick EE as a major? And our students see the beauty of this discipline. It's that it's combining math and physics with other sciences. It's very broad. The fact that it spans everything from applied math to physics. The knowledge that you learn is rewarding and easily expandable. It's broad major. It's BOM. I don't know what that means, but I think that's good. And then there was one honest student who said, I didn't know what else to do, so I majored in EE. Okay, so then what is EE? This is actually on the department website. I think it's a word cloud of all the research that all of our faculty do. And if you look at this, you say, well, how do I pull something out of that I can describe electrical engineering? Now, I'm an optimist, and I believe in world domination. So I think we should just say EE is the design and analysis of any system or component that uses electricity. That's everything. Okay, so I think that we should own, or we might share, co-own, all the systems and components through which electricity flows. That's everything. 125 years from now, we'll be on 13G when it comes to cellular systems. How can we not own data science? We've always been about information and information technology. Energy systems, absolutely, there's a lot of electricity there. Automation. MedTech absolutely should be owned by electrical engineering, quantum computing, and on and on. So if we think of electrical engineering as the core of any system that electricity flows through, we have a really bright future, right? We own everything, or co-own, perhaps. But there are a few dark clouds. So threats, I think complacency. When I came to Stanford in '99, I'd been at Caltech for 6 years, so I came and I officially started over, so it was a 4-year appointment with a 3-year renewal. I remember Jim Plummer was the chair, and I said, you're really going to make me work another 7 years to get tenure? And he said, well, we can't promise you anything. So I came here, and the first word that came to mind after a couple days on the Stanford campus, so I'd been at Caltech, and I thought, okay, moving, it's going to be harder at first, but I like being in a bigger place, and I think long-term it'll be better. Stanford was better for me from the day I walked onto this campus than Caltech, and the reason is it was a non-complacent place. When I talk to people, I remember Bob Dutton came to my office within a couple days, and he's like, oh, I'm working on this great project out of CIS, and you should apply for some seed funding. And I thought, Bob Dutton, he could just rest on his laurels. He doesn't need to be, doing this new project. Nobody here rested on their laurels. This was a non-complacent place. So if we are complacent, we will not be able to realize this future. Fear. Are we fear of being no longer the most relevant department in engineering? Fear of CS taking over. Fear of failure. We would never be Silicon Valley if our engineers were afraid of failing, because you don't start a company if you're not going to take the possibility of failing. Failure to lead, I think Jim gave that discussion very well in his talk. And I will say, another Jim story, when I was asking about coming to Stanford, and I said, okay, you're going to make me go another 7 years officially to get tenure, so that's 13 years to tenure. That's fine, but I think I understand what I need to do to get tenure. What do I need to do to become a full professor beyond that? And Jim said one word, leadership. We were looking for leaders in Stanford EE. And so I didn't ask for, okay, what do you mean by leadership? But it was very clear that that's what it took to be successful at Stanford, with leadership. And the other thing, Stephen alluded to this in his talk early on when he talked about how many women faculty we've had, and that it's not a great story, and Christina Johnson also did. I think lack of diversity is a threat to EE and to engineering, and that's why I spend so much time on it. So why is diversity important to EE's future? Is it just for political correctness reasons? Is it because we don't like to show that chart with very few women faculty members on it? I truly believe it's about success. So it's well documented that diverse organizations are more creative, perform better, and have higher satisfaction, not just of the diverse members, but of all the members in the organization. If we're going to make electrical engineering as this broad-minded, ambitious discipline thrive, we need to attract, retain, and engage diverse members and make sure that they achieve their full potential. We're struggling to attract diverse members, and in fact, the retention of women EEs in industry is under 50%. Diverse leaders serve as role models and mentors to bring those diverse people into the profession, and they also add diversity of thought, not only to engineering design, but also to leadership. And we want to make things better for the next generation of diverse technologists. And this was abstract for me 5 years ago, but my daughter is studying mechanical engineering, and I want it to be better for her. So is it better for her? Is it better for this generation of diverse students? Well, the percentage of women undergraduates in electrical engineering is 16%, so that's really not critical mass. In engineering overall, there's more, but it's still only 20%. 16% across the country of EE faculty are women. Stanford is way behind. Okay, we're at 12%. Not only are we behind nationwide electrical engineering departments in percentage of women, we are way behind at Stanford. We are second from the bottom out of 71 departments in terms of the percentage of women faculty that we have. We have never had a diverse person in leadership in EE, not just department chair. And by the way, we're the only one of the top 5 departments in EE that hasn't had a woman chair. But leadership requires grooming. You have to groom leaders. You want to put them in, young people in leadership positions early on. And we've never had any of the important committees in the department chaired by a woman or a URM. In industry, workforce is low, and women leave at a higher rate than they come in. This statistics always surprise people. Less than 3% of patent holders are women. And okay, so I've done 2 startups. Only 10% of Bay Area Series A startups had a woman founder. And when I was pitching dozens of pitches to VCs, everyone else, all the other women in the room were serving coffee. There were no women sitting around the table deciding whether my company would get funded. The NASEM report, which talks about sexual harassment as a threat to engineering. And sexual harassment isn't the egregious, somebody attacking you. It's the gender harassment. It's the view that negative views towards women who challenge traditional gender roles. EE did a survey and found, something similar to what the National Academy of Engineering did. 73% of women in the IEEE, this was 5,000 women across all of the IEEE, said they had negative outcomes in their career due to their gender. So it's no wonder that women leave. And by the way, IEEE didn't want to publish this data. They said, well, we don't want to demoralize the women. And I said, well, we know what's happening. So if you're transparent and publish it, then we can do something about it. So that's not a happy picture for where our profession stands with respect to diversity. Maybe because I did all my degrees at Berkeley, I'm quite an activist. And in particular in the IEEE, I did take on this role to chair diversity, inclusion, and ethics. You've wondered why ethics? Well, all the sexual harassment stuff came to me because if we can't do anything about that, then we're never going to have a diverse and inclusive profession. I wrote an implicit bias briefing together with Dave Messerschmidt at Berkeley on IEEE awards because it was very clear that women were not only not winning, but they weren't even nominated. This year, 5 women won major IEEE awards and honors. So it took 4 years, including our colleague Teresa Meng was one of these, but it certainly has had an impact. So I think there's a lot of work needed on diversity and inclusion. We need the guys. You're the majority. We can't do it on our own. And these activities have to take place in professional organizations like the IEEE, which is the largest professional organization, universities and companies. So I'll just say happy birthday to my wonderful department. It's been an amazing place to build my career. It's still young to me. You still look young to me, EE. And I hope there's another 125 years of success. Thank you.